We're about to begin. May I ask you to take your seats? It's 8:30. Welcome to the second day of the ISIT. I'm Alexander Barg, co-chair of the Technical Program Committee. It is my pleasure indeed to welcome you to this conference. I hope you're enjoying it as I am so far. I think it's coming out well. And I'm very pleased to introduce this second day with an exciting talk of Alexander Vardy. Let me give him a brief introduction. Alexander Vardy is a professor in the Department of Electrical Engineering, Department of Computer Science, and the Department of Mathematics, all at the University of California, San Diego. Many of us know him personally, but also by publications, of which he has over 100. He has also numerous patents, most of them in the general area of coding theory and practice. He received numerous awards, and this is really an appropriate time to recall some of them. He received the Rothschild Fellowship in 1992, the IBM Invention Achievement Award in 1993, the Xerox Award for Faculty Research in 1996, the IEEE Information Theory Society Best Paper Award, jointly with Ralph Kotter, in 2004, the Best Paper Award at the IEEE Symposium on the Foundations of Computer Science in 2005, and the Fulbright Fellowship in 2006. He is a Packard Foundation Fellow and a Fellow of the IEEE, the Institute for Electrical and Electronics Engineers. During 1995-2001, he was first Associate Editor for Coding Theory and then Editor-in-Chief of the IEEE Transactions on Information Theory. He currently serves on the editorial boards of the SIAM Journal on Discrete Mathematics and on the Board of Governors of the Information Theory Society of IEEE. Well, he's also a friend of many of us, myself included. He speaks many languages. He speaks Russian, Hebrew, French, and some Japanese, also he says. So you're encouraged, those conversant with those languages are encouraged to ask questions in those languages to really check that. But the talk itself will be given in English. Alex.
Well, thank you so much for the introduction, way too long. I hope that by now all of you have had a chance to read this disclaimer, and that's very serious. Look, I'm trying in this talk to give a grand overview of coding theory from past to present to future, and this is clearly impossible. And I guess what I'm going to do is present a very personal view of what coding theory is or has been to my mind, and so please don't make any conclusions. All right, so here's the story of coding theory in one slide. As everything else in information theory really starts with this paper of Claude Shannon, and of course I mean the channel coding theory, which non-constructively shows the existence of utopia. Now, unfortunately or fortunately, Shannon did not tell us how to find codes that achieve capacity or how to decode those codes efficiently. And that's really trying to answer this puzzle is what coding theory has been doing for the last 50 or 60 years. And since 1948, we took a long and winding road towards this goal. We don't know yet, really. This road called Algebraic and Combinatorial theory, coding theory, we don't really know yet if it leads to the capacity promised by Shannon. But we certainly saw many beautiful views along the way. And then, some 10 years ago, we discovered a magic solution, which sort of flies over the hills and gets directly to the capacity. We don't yet quite understand how this magic carpet works, but it certainly gets there. Yeah, of course, I mean turbo codes, LDPC codes, and general codes defined on graphs with iterative decoding algorithms. This is a remarkable idea. We get codes that are on one hand random enough to get close to capacity. On the other hand, these codes can be decoded in linear time. And that has led to thousands of papers. The tools in this field are mainly probabilistic. They're not algebraic or combinatorial. So that's why I'm calling this the probabilistic coding theory. Well, let's review the remarkable progress towards Shannon limit that was enabled by these methods. So the original turbo codes introduced by Beru, Glavieux, and Tishimashima, they're about 0.7 dB from capacity. And then there was a breakthrough paper of Richardson and Urbankia, which showed us how to design irregular LDPC codes that get to about 0.1 dB from capacity. Well, what if we want to get closer? How about 0.01 dB from capacity? Well, that can be done. Well, what if we want to get even closer, 0.001 dB? That also can be done. So really, an inevitable conclusion from this is that for all practical purposes, we have already solved this grand puzzle posed to us by Shannon. And we have achieved the capacity. Well, I see it's very early, but there's already a question from the audience. Aha. Is coding theory dead? Well, that's a very good question. Thank you for asking this. Well, how can I possibly answer such a question? Well, I thought I would do this in the words of Bob McLeish. This is a true story. The emphasis is mine, but the rest of it is taken verbatim from something that Bob actually wrote. So he tells of the story where he was asked the very same question in a very same setting. So what would Bob, are you here? What, well, okay, let's see what he would have answered. And that's Bob's answer. So he says, at least in his view, by now, turbo codes, LDPC codes may be senior citizens. But there are other parts of coding theory that are still very young, and he talks about ReedSolomon Codes as the prime example. So that's what I'm going to do in this talk. I'm trying to make an overview of those parts of coding theory that, to my mind, are forever young. And we'll start with revisiting three classical problems that go back 50 years or more. And I think it's amazing how, from very simple bounds, we get to very deep conjectures that are still unsolved. We'll then get to the present. So we'll talk about recent advances in decoding ReedSolomon codes. This is a very active field right now. There are great results being obtained. Well, some of them were obtained just a few months ago, and we'll talk about them. And then we'll talk about connections to other areas and really new stuff. So I'm not sure if I'll be able to cover both topics, but this is really the future in many ways of coding theory. And then, of course, there is much, much more that necessarily I will have to skip in this talk. Well, let's get going. So this is the first part of my talk, which maybe the appropriate title is What's Old and Exciting in Coding Theory. All right, well, we'll see three bounds and three conjectures. And we start, however, with Hamming. Algebraic and combinatorial coding theory really does start with Hamming. He set up the framework wherein we work. He did so by defining a metric on the space of n tuples over some alphabet, which is the well-known Hamming distance. And then the minimum distance of the code can be defined. And then we could think of a code as simply a packing of spheres. So really, in this framework of Hamming, coding theory becomes the science of packing spheres densely in metric spaces. All right. Well, if so, we could ask, what are the best codes in this framework? Let's introduce some notations. So we'll use the well-known, the accepted notation. A, Q, and D is the largest number of vectors of lengths n over an alphabet with Q letters that are, every two of them are D apart. And we'll use this for the volume of the Hamming sphere. And really, one of the very first results in coding theory is this bound due to Ed Gilbert and later improved by Varshanov, which says that the size of the best code is at least as large as the ratio of the volume of the whole space divided by the volume of the sphere of the corresponding radius. That's a really fundamental but simple result. It can be proved in a few seconds, so let's just do that. Here's one of the many proofs of the Gilbert-Varshanov bound. This goes by a greedy construction algorithm. So what we do, we start with the space, we pick an arbitrary point, cut out a sphere of radius d minus 1 around it, and as long as there are other points left in the space, we just keep doing this. By virtue of cutting out the spheres, we guarantee that the distance of the code will be at least d. And we'll keep doing this until there's nothing left. Well, when there is nothing left, that means the spheres have to cover the entire space. So the number of centers, and these are our code words, times the volume of the sphere has to be larger than the volume of the space, and that's it. That's the Gilbert-Varshanov bound. So it's a very, very simple result, very, very simple proof, and I think it's amazing that we still do not know how to improve upon this result asymptotically, at least in many important cases. So that's the first open problem that I'd like to pose today. I will pose 3 classical problems in coding theory, and that's one of them. All right. Well, what about asymptotic improvements of the Gilbert-Varshanov bound? Well, some of them are known, and the first one is due to this work of Zwatzman, Vladut, and Zink, which really introduced the full force of algebraic geometry into coding theory and enabled improvement of the Gilbert-Varshanov bound, at least for certain rates and distances. This, in fact, has been recently improved by 2 other authors. This is very new work. But unfortunately, all of this works for large alphabets. When the alphabet is small, in particular a binary alphabet, still, asymptotically, we have no improvements whatsoever over the Gilbert-Varshanov bound. Okay, so let's look at the binary case, which is really, in many ways, the most important one. The Gilbert-Varshanov bound itself takes a very simple form, and we arrive at this conjecture that the bound is, in fact, asymptotically exact for binary codes. There's been a proof published for this conjecture. Unfortunately, this paper is less than a page long, and there's really no room in that paper to present a proof. But anyway, so really, the problem I'd like to pose is this: prove or disprove this conjecture. This is one of the key conjectures in coding theory. Well, let's see a recent result which is very much related to this conjecture. So here's the first ever asymptotic improvement of the Gilbert-Varshanov bound for the binary case. This is a scary looking formula, but you don't need to worry about this. This will see just a number of edges in a certain graph, and this is the result. This is the Gilbert-Varshanov bound, and this is a factor. It takes quite a bit of work to show how does this factor behave asymptotically, but it behaves linearly in n, so it's a true asymptotic improvement. In fact, the proof of this theorem is not very difficult. So let's try to prove it in one slide. So we'll start by a definition. We define a graph which, as an homage to Ed Gilbert, we called it the Gilbert graph. And it's very simply the vertices of this graph are just the binary vectors of length n, and we connect 2 of them by an edge if their distance is less than d. And this is an example of such a graph for n equal 4 and d equal 2. So it's obvious from the definition immediately that this quantity that we're interested in is simply the independence number of this graph. Okay, that should be completely clear. Now we use a well-known, a classic result in graph theory, which is due to ISIT, Komlosh, and Semerady, which gives a powerful lower bound on the independence number of a graph in certain cases. So we need a graph with a few triangles, and so this is the number of triangles. This is the asymptotic improvement that we will get, which is the degree of this graph. So really, what remains to prove the theorem is to count how many triangles there are in this Gilbert graph. In this small case, you can see there's plenty, but it turns out, luckily, that as n grows, this graph becomes what's called locally sparse. So the number of triangles asymptotically is negligible with respect to the improvement we get. All right, so that's precisely the theorem that we have seen on the previous slide. Well, how does this result relate to this famous conjecture that I just mentioned? Well, it really depends on the interpretation. At least you have to be now very careful in phrasing this conjecture. So there really may be two ways that there were no distinction between them until now. Here is one way to say so. So the Gilbert Varshanov bound on the size of the code is asymptotically exact. That would mean something of this sort. And we show that this is certainly false. Okay, we improve upon this function by something linear in n, so the limit cannot possibly exist. In fact, we have something like this. However, the more common way to phrase the Gilbert Varshanov bound is in this way, where it relates to the rate of binary codes. We take this divided by n, then this improvement that we have log n over n will go to 0 asymptotic. So in this sense, there's still no improvement, and very well, this conjecture very well might be true. Okay, so it is an open problem. Okay, let's get to a second classical bound in coding theory, and that's the Hamming bound, or the sphere packing bound. And really, the proof of this is right in this picture. You can't pack more spheres, hard spheres in a space than would fit. That's all this bound says. And really beautiful cases result when this bound is achieved with equality. Then we have something called perfect codes. Well, we could ask what kind of perfect codes are out there. There are 3 trivial ones, and there are non-trivial ones. In fact, the binary Gole code is really pretty much the only non-trivial one. It's an amazingly beautiful structure. And one of the key achievements of classical coding theory was complete classification of such perfect codes. So this theorem, due to Van Lien, Tietewijn, and others, shows this is it. These are all the perfect codes. They do not exist anymore. So we know all we want to know, all we can know in many ways about binary perfect codes. But what if we look in different metric spaces? So let's consider, instead of all binary vectors, let's consider binary vectors of constant weight. Then you could define what's called a Johnson space, and you could get a form of a Gilbert Varshanov of a sphere packing bound in this space, which looks like this. And once again, codes that attain this bound with equality would be perfect code in the Johnson scheme. And again, there's 3 trivial cases. And what about non-trivial ones? Are there any non-trivial perfect codes in the Johnson space? Well, here comes Philippe Delzard, one of the most profound contributors to the field of algebraic and combinatorial coding theory, and in 1973 makes this conjecture that there are no non-trivial perfect codes in the Johnson metric. And this is the second problem that I would like to pose today, which is prove or disprove this conjecture. And before you rush to do that, let me just point out that lots of people worked on that already. It's a very difficult problem. And again, this is very young. Just a couple of years ago, we had what I think is a breakthrough result on this problem, which basically says that for many different radii, there could be only finitely many non-trivial perfect codes, so you could pretty much enumerate them. And then for the first 3, they show there are none. Okay? And not only the result is interesting, the proof of this result is also very nice. What they do is introduce a certain polynomial, which is a counterpart of the Lloyd polynomial used for the study of perfect codes in the Hamming metric. And then they use this polynomial in a very similar way to show non-existence results in the Johnson space. All right, the third bound. And that's probably the simplest bound of all. This is the Singleton bound. And again, all you need to prove this bound is just this picture. Yeah, I'm not going to go through the proof. I think it's completely obvious once you look at that. And again, codes that achieve these bounds with equality are called MDS. And well, what about MDS codes? Well, it turns out there are plenty. In fact, if you take a random linear code and let the size of the field grow, then with probability 1, it will be MDS. And of course, there are the ReedSolomon codes that are MDS. We'll talk about them later quite a bit. Okay, so MDS codes have many wonderful properties. We know quite a lot about them. Here's the list. But amazingly, what we don't know is what about their lengths? So this is a subject of what's called the MDS conjecture, which is pretty much explained by this picture. It says if you take the dimension of the code and the codimension, there are some would be the lengths. Where you see the dot, the code exists. This line here says there's a bound which says the code could not exist, and this is the conjecture, that pretty much the codes have to lie, all of them, below this line. This is still very much unsolved, and interestingly enough, this has connections, deep connections, to many areas of mathematics. So there's equivalent conjectures in linear algebra, in matrix theory, in orthogonal arrays, in projective geometry, and so on and so forth. It's a very deep problem. There is not much known about this problem. There are certain cases that have been solved. Again, this is classical. This has been worked on for some 50 years. So this is the third problem, the third open problem that I'd like to pose today. Prove or disprove the MDS conjecture. Well, all right. So what is this? This is the brand new Atkinson Hall on the campus of UCSD. And, well, why I'm showing this? This houses the brand new Center for Information Theory and Applications. And what does that have to do with our lecture? Well, this center will sponsor prizes for the solution of important problems in information theory. And I'm hereby proud to announce the first 3 prizes. They will go for the solution of the 3 problems that I just mentioned. All right, well, maybe we should ask the question, what are the practical applications of these problems? And, well, I'm sorry to disappoint you, Alon, but the best answer I could give is right there. Okay, second part of my talk. This has to do now with recent advances in algebraic list decoding of ReedSolomon codes. Okay, as opposed to the previous overview that I gave, this, in fact, is very, very practical. ReedSolomon codes are, again, over 50 years old, but they are forever young. If you look at the number of circuits that are used today to decode any kind of error-correcting codes, then a very fair estimate that at least 3/4 of them decode ReedSolomon codes. Well, if you are in this audience and you still don't know the definition of ReedSolomon codes, then shame on you. But let me remedy this misfortune in 30 seconds. Okay, so here it is. So we define the code by its encoder. We take any k arbitrary information symbols and think of them as a coefficients of a polynomial. And then we simply evaluate this polynomial at some n fixed elements of the field that have to be distinct. And that's it. That's the ReedSolomon code. It's very easy to see that this evaluation map is linear. It's very easy to see that the dimension is k, the length is n, and the minimum distance follows simply from, fundamental theorem of algebra. A polynomial of degree less than k can have at most k minus 1 zeros. That means n minus that have to be non-zero, and that gives you the minimum distance of the code, which achieves the Singleton bound. So ReedSolomon codes are MDS. Well, what can we say about decoding ReedSolomon codes? Well, by definition, we could think of every code word as n values of some polynomial of degree at most k or less than k. And simply by interpolation, we can recover this polynomial from any k of its values. Well, so this means that a ReedSolomon code by this univariate interpolation approach will always be able to correct n minus k erasures, and it's really not that difficult to get from here to half that, the number of errors. There is classical algorithms. The most well-known of them is Berlekamp-Massey algorithm, which is really just a very efficient way to perform this interpolation by looking at what's called an error locator polynomial. And that's what all the decoders, or most of the decoders for the ReedSolomon codes do today. So this is clearly the best possible. How can you possibly reconstruct a polynomial of degree k from less than k values? Well, or is it? So we should all be grateful to Madhu Sudan, who showed to us just a few years ago that ReedSolomon codes can correct many, many more errors than we thought possible. So this is a recent breakthrough work. Let me explain well, this is Madhu Sudan showing off his Neven Linna Prize. Well, here's the d over 2. This is the Singleton bound divided by 2. This is the classical decoding. And the first paper of Sudan for low rates shows that we correct many, many more errors. And then Guruswamy and Sudan have improved this to a decoding radius of 1 minus the square root of the rate, which then improves on the classical decoder for all rates. And what is shown here is the ultimate limit. That's 1 minus the rate. And obviously, you cannot do better than that. There's many easy ways to show this. OK, so let me give you a brief idea of how this works. So as I said before, we could think of ReedSolomon code words as polynomials of degree k. The transmitted code word that we don't know, we can think of this now as a bivariate algebraic curve of this form, whose degree is at most k minus 1. And what becomes important is this classical theorem of Bézout, which says that if you have curves of degree d and delta, they will, if you count the number of intersections properly, they will always intersect in the product of the degrees number of points, and will not intersect in more points unless they have a common factor. And this is this exception that is particularly important for what we're trying to do. So this is, really, in a nutshell, the application of this theorem for the decoding of ReedSolomon codes. So suppose we could somehow construct a bivariate polynomial which defines a curve of a certain degree that intersects this unknown curve in more points than the product of the degrees. Then by this theorem, this polynomial, this curve that we have constructed, and this curve that we want to figure out, they must have a common factor. But this is irreducible. It's a prime polynomial, if you will. So the only way for them is to have a common factor if this itself is a factor of q. And then having q, we could simply factor out the transmitted code word. So that's the basic idea. And again, Bézout's theorem is the underlying backbone of all this approach. And at this point, I just couldn't resist from these two quotations. The first of them is due to Hardy, which says real mathematics of real mathematicians, Fermat, Euler, Gauss, Abel, etc., and Bézout in this list is wholly useless. And yet, today, as we speak, Bézout theorem is being used to decode ReedSolomon codes. This is the first application where this type of decoder has been used, and there's probably or hopefully going to be many more. All right, so let's just give some insights into how this would work. So this is a toy example, but I think it's quite illuminating. So suppose the dimension is 2. So the code words are really lines. They're polynomials of degree 1. And suppose that we have somebody gave us 14 points through which we want to interpolate. How these points are given, I'll talk about that later. But OK, so now we want to find all lines that pass through at least 5 of these points. How shall we do that? This is how Sudan and Guruswamy do that. So they first compute a bivariate polynomial that passes through all the points. And they insist that the degree of the polynomial is strictly less than this required number of intersections. And it's not difficult to show that such a polynomial will always exist. This is what it is in this example. Now, we, by construction, know that it passes through all of these 14 points, but it has more zeros than just those 14. So let us plot all the zeros of this polynomial. And as we do that, magically, the lines that we're looking for emerge. These are the zeros of this polynomial. Mathematically, this happens because this polynomial factors in the following way. So you can see the factorization. These are the 2 lines that we're looking for, and that's the circle. And it's not just a coincidence. The Bézout theorem tells us that it must be so, because the product of the degrees, look, this one has degree 4. The degree of this line is 1. Their product is 4. They intersect in 5 points by construction. So by Bézout's theorem, this must be a factor of this polynomial. So this is really the underlying idea of interpolation-based decoding, the underlying idea of the approach of Guruswamy and Sudan. OK, but in practice, it's a bit more complicated than that. The decoding algorithm consists of 3 steps. So the first step is how to find those interpolation points. Then once you found them, you need to interpolate. You need to compute the polynomial that passes through them, and then factor it, or at least find certain factors. Now these steps have very different meaning. The first step, usually computationally, is not expensive at all. But this is the one that determines the performance of the decoder. Once you fix the interpolation points and the multiplicities with which you will go through these points, the output is determined. And then this determines the complexity of the decoder. This is the computational bottleneck. And a lot of clever ideas have gone into optimizing this. Unfortunately, I really have no time to talk about this, but I will talk about the first step a little bit, the multiplicity assignment. Okay, so and this brings me to the subject of algebraic soft decision decoding of ReedSolomon Codes. So this is a plot of a performance which shows potential gains due to such soft decision. And really the key idea of a soft decision decoder is to use the probabilistic information that we usually have at an output of a channel. In hard decision decoding, we simply throw this information away at the very first step. So in order to do that, what we need is some way to convert the probabilities that are observed at the channel output into algebraic interpolation conditions, into those points for which we will interpolate, and the multiplicities with which we'll interpolate through these points. And this is how we propose to do that with Ralph Cotter in our paper. So first of all, we showed that the number of intersections that we want to maximize is really a random variable whose distribution will depend on both the channel observations and the way we assign those interpolation points. So one could ask, well, what is the assignment that will maximize the expected value of this variable? And that is the assignment that we have found. So basically, it's really very simple. We take a matrix of channel reliability. So this matrix tells us it has n columns, and these correspond to positions in the code. And each column is a probability distribution, which tells us how likely is each symbol to have been transmitted in this particular position. And we simply take a proportional assignment. We just scale that and take the floor, and that's the assignment that we propose. And then we have this theorem, which says that the probability of decoding failure can be expressed as the probability that this random variable is below a certain threshold. And we show that this particular assignment maximizes the mean of this random variable once we fix the threshold. So if this is the distribution that we get for the score by virtue of this assignment, it's guaranteed that any other distribution will have a lower expected value. Now, this is not necessarily the optimum thing that we want. So in some ways, the problem is still open, how to really assign multiplicities to minimize this probability. Okay, but that does lead to very nice performance, nice results. And so this is a plot for a very real code. This is the type of code that is used today in magnetic recording. And you could see nice gains. But you could ask, well, is it feasible? And the answer is yes, it's very, very feasible to do this thing. What we see here is a detailed VLSI architecture for actually a longer code than that. This architecture is designed to run at 3 gigabits per second, and the total hardware cost of everything comes out at about maybe 3 to 4 times that of just a conventional Berlekamp master decoder. Okay, so this is very much practical stuff. Okay, well, this is not all. There is much, much more in this area. And in particular, there is interesting result that, or several interesting results that were obtained just a few months ago, less than a year ago. And what they have to do was decoding beyond the Guruswami-Sudan radius. So Guruswami and Sudan showed us that we can decode that much. And since 1999, this was the best known. There's really no way known to ever exceed this bound. And now we can. And the key idea here is sort of summarized in this row. So look, what Guruswami and Sudan did, they basically transitioned from univariate interpolation decoding to bivariate interpolation decoding. And by virtue of that, they corrected more errors. Well, why not try to decode in 3 or more dimensions and see what happens? Well, more precisely, this leads to a new family of codes. So these are no longer ReedSolomon codes. In fact, they are nonlinear codes. And this is how they are constructed. The first step is exactly the same as we would do in ReedSolomon decoding. In ReedSolomon coding, we form this polynomial f of x. But the second step is crucial. Given f of x, we compute another polynomial which is completely determined by f of x in simply this way. We take this polynomial to a certain power. This integer a is an arbitrary parameter. It just has to be large enough, but otherwise it's completely arbitrary. And then we take that modulo some irreducible polynomial of degree k to get back a polynomial of degree k. Now we have two polynomials, and what we will evaluate is sort of a linear combination of both. We take a basis, 1 alpha, any basis for fq squared over fq, and this will be our transmitted code word, where x1 through xn are the same as in the case of ReedSolomon codes. Okay, so now how do we decode this? Well, suppose this is what we receive now from the channel, and one crucial observation is that now this is a trivariate interpolation problem. We have x, y, and z that come. X is the evaluation points. Y corresponds to f of x. Z corresponds to g of x from here. Okay, so it's the same form, yi plus alpha zi. Okay, so now we will interpolate through this sequence of points. We're not doing soft decision here, although it can be done. But let's say we just interpolate with a fixed multiplicity, same multiplicities for all of them, and we somehow get this trivariate polynomial. Now, it's easy to show that if the number of errors is not too large, this polynomial satisfies a condition very similar to the condition of the Guruswami-Sudan decoder. So, okay, so here's the transmitted code word that we don't know. We have interpolated through the received word, and we have basically obtained this two-dimensional surface in 3 space. The problem is that the number of lines or one-dimensional curves on the surface is large. In fact, in most cases, it's going to be exponential. So that's where this encoding operation comes into play. So now we realize that we have not one but two relations between that f of x and g of x satisfy. This is one of them, and that's another one. This is the encoder polynomial. We know this a priori. So now what we can do is intersect these two surfaces. And the second surface, the encoder polynomial, has been chosen in such a way that it guarantees a nice intersection. These two surfaces will never coincide. The number of lines that belong to their intersection will always be small. Okay? So that enables us to recover the information. And what's the outcome of this? Well, the outcome is pretty amazing. It's due to another important work by Guruswami and Rudra that basically takes these ideas that I have just described and sort of folds them back into ReedSolomon codes. But really, this is the basic idea that we just followed. And the result is that we can decode up to 1 minus r. So this is the ultimate bound. We can do that in polynomial time. So really, in an important way, the key problem of list decoding has been solved. We can construct the best possible codes, list decodable codes, in polynomial time. We can decode them in polynomial time. The situation is much better than what we know in unique decoding. There we have the Gilbert Varshanov bound, which we don't know if it's tight or not. We have no way to achieve it. We don't know how to achieve this bound in polynomial time. Certainly don't know how to decode. Well, this does not completely resolve all the problems. There are still many issues that remain. Well, one of them is that the alphabet size required for these constructions that achieve this decoding radius is very large. The other is that the list size now is no longer constant. It grows with the code lengths. It grows polynomially, but it does grow. So all this, I think, can and should be improved. And if it is improved, my conjecture is that these methods will enable us to get to the capacity of a Curie symmetric channel with a complexity that is better than anything currently known. All right. Well, that's ReedSolomon codes. And now I get to the third topic of my lecture. And this is applications of coding theory in theoretical computer science. Well, let me ask you the following question. Which conference other than the ISIT had sessions on coding theory annually for the last 5 to 10 years? Well, this is not ITW. This is not Asymptotic. These are conferences that I actually just mentioned on the previous slide, the Fox and Stock conferences in computer science. The community of computer scientists really thinks of coding theory as their own. Well, there's lots and lots of important applications of error-correcting codes in computer science, and most of them hinge on these two types of codes. They're known as locally decodable codes and locally testable codes. And in a nutshell, these are codes that you can decode in sublinear time. The applications of locally decodable codes are decodable in linear time. Locally testable codes, you can do error detection in sublinear time. There's numerous applications, private information retrieval, generation of pseudorandom bits. This one is a particular application that we'll talk about in detail later today. All right, well, hold on a second. How can you possibly decode in sublinear time? In sublinear time, there is not enough time to read the input or write the output. So this is clearly impossible. Well, this is an actual quote from a good friend. It's a little bit brash, so I didn't want to mention his name. Anyway, so yeah, so in the next few slides, let's see how to do the impossible. Okay. To do so, let's discuss a particular application of locally decodable codes. It's actually a very important application. Okay, it has to do with what's called hardness simplification. The key question is this: how hard is it to compute a Boolean function? And there are two sort of notions of hardness that are very, very different. There's something called worst-case hardness, which means that no polynomial time algorithm can ever compute this function correctly on all possible inputs. There's at least one input for which computing this function is hard. And all of the class of NP-complete problems are believed, well, if NP is not equal to P, they are believed to be worst-case hard. But really, this is not very useful because, you know, there could be very few inputs for which the computation is hard. Much, much more useful, much stronger is average case hardness, where we guarantee that no polynomial time algorithm can compute the function correctly on some fraction of the inputs. And hopefully this fraction would be small. Now clearly this fraction cannot be too small. It can never be less than half or even equal to half, because random guess is a polynomial time algorithm which will compute the value of any function correctly on half the inputs. Just flip a coin. All right? So, but still, you know, fractions of delta preferably close to half would be nice to have. And this has numerous applications. It's easy to conceive that such functions that are hard on the average will be important in cryptography. They're actually very, very important in pseudorandom number generation. So here is our goal. That's what we'd like to do. We'd like to convert a function that is worst case hard into a function that is average case hard. How shall we do that? And this is done using error-correcting codes. So this is in a nutshell the whole idea. Interestingly, the error-correcting codes encode truth tables of the functions. Okay, so we take, somebody gives us a function which is worst case hard. We take the truth table of that function and code this with a certain error-correcting code, and we claim that the resulting code word is a truth table of a function that is now delta hard. Well, why is it so? Well, suppose it isn't. Suppose there is some polynomial time algorithm that computes g correctly on some delta fraction of the inputs. So this polynomial time algorithm, we could use it to produce sort of an error-corrupted truth table. So it coincides with g on some positions. On some positions, it's different. Now we'll use the decoder for this error-correcting code to correct all the errors introduced by this algorithm and reconstruct the truth table of f. So if the error-correcting code has certain required properties, and we'll talk about them in a second, then this entire box, assuming the existence of an average case polynomial time algorithm for G, this box becomes a worst case polynomial time algorithm for F. But that's a contradiction by assumption. We assume that F is worst case hard. So that's sort of the key idea. Now, what's interesting is the properties that are required of the error-correcting code. So these are very, very strange codes for us. Okay? They're nothing like what we're used to seeing. So first, let's look at the lengths and dimension, the rate of such codes. So they're both, remember, we're coding truth tables. So we're taking a function of n variables, converting that to a function of m variables, where m is slightly larger than n, let's say 1.1 times n. But the lengths and the dimension of the code are 2 to the power of that. So the rate of the code is behaving like this. It's exponentially low. As n grows, this approaches 0 exponentially fast. Well, what about error correction radius? If we want to get delta close to a half, then we need to recover that many fraction of errors. And for binary codes, just by the Plotkin bound, it's easy to see this is possible only with list decoding. Unique decoding can never get beyond 1/4 of a fraction of errors. And the key property, and that's really the most important one, is the decoding complexity. Look, in that scheme that I just showed, how would the decoding go? Well, okay, we take some input to F, and we encode this. We use this hypothetical polynomial time algorithm for G, which gives us possibly an error-corrected answer for X. Then we decode this, and we get the value of the function. Now, this needs to be a polynomial time algorithm. Otherwise, the whole construction makes no sense. And for this to be polynomial in n, the number of variables, this needs to be sublinear, well, polylogarithmic, in fact, in the lengths of the code, which is exponential in n. So that's where sublinear time decoding comes into play. That's where it is important. Okay, so now is the key. How can we do that? And what makes this possible is the observation that all that the decoder needs to do is produce one bit. It only, on input x, given a particular input, it needs to tell us the value of the function. Is it 0 or 1? Okay? So that's really what makes it possible. So that brings me to the definition. This is a formal definition of locally decodable codes. There's going to be 3 parameters. Q is the number of bits of the input that the decoder is allowed to read. Usually that Q is a constant, 2, 3, 10, a small number. Delta is the sort of the distance, you know, how many errors can you correct? And P is the probability with which you correct an error. It's sort of easy to see that if you read only 2 bits from the input, then with certain probability, they both could be an error. So you can never guarantee a correct reconstruction, but you can do so with a certain high probability. So these are the 2 properties that define the code by its decoder. So an input is some error-corrupted word y and a particular index, which tells us which bit of the message we're required to produce. Then we read some q bits of the input. Usually it's done uniformly at random, and produce the output, that single bit. And then with probability at least p, if the input y agrees with the code word that corresponds to the message in at least that many positions, then the probability of a correct answer has to be greater than p. So q, delta, and p, these are the parameters. Okay, so this is the key open problem in a locally decodable code. So given these parameters, q, delta, and p, what is the best possible trade-off between n and k? All right? Well, let me give you an example. This all looks rather strange. So here's a code that we all love and know and cherish, which is simply the first-order read-Muller code that turns out to be locally decodable with only 2 queries. Okay? So this is a theorem. Let me show you how this works. All right, so this is a binary first-order read-Muller code. It's very similar to ReedSolomon codes, except now we take linear polynomials in many variables. Okay? So instead of taking a polynomial of degree k, we take a linear polynomial in k variables and then encode the message u into the coefficients of this polynomial. And the code word is again an evaluation of this polynomial. Now we evaluate, so there are k variables, so we evaluated all possible binary k tuples. Okay, that's the first order Reed-Muller code. All right, how would the decoding go? And this is local decoding. So suppose we have some code word corrupted by errors. This is our input. And in addition, we're required to produce bit I of the message. This is also part of the input. What we'll do, we choose X. We choose this X uniformly at random, and we'll read only 2 bits only from the input Y. Which ones? Those that correspond to this X that we selected uniformly at random, and X plus another vector. And this vector is the one which has a single non-zero entry, a single 1, at the I's position. Okay? So these are the ones that we'll read from the input. So let's say we read 2 bits. One of them is, corresponds to X, the other to the X plus offset. Both of them could be an error. Now let's assume for a moment that both bits are error-free. What happens then? Let's take their sum, and their sum can be written in this way, quite obviously. This is the evaluation at X. This is the evaluation at X plus the offset. When you add the 2 together, everything cancels out except exactly the I's bit of the message that we're required to produce. Okay? So if A and B, those 2 bits that we have read, are error-free, we're done. But now it's easy because we just look, what's the probability that those bits are error-free if at most 1 minus delta fraction of positions are in error? Remember, we choose X uniformly at random, so that does make sense. So these probabilities are clearly at most 1 minus delta, and you could compute the probability of, when their sum is correct, and that comes out to be all right. So as long as you can reproduce the bit in an error-free case, in this case, just simple analysis shows you that you can also recover from errors with a sufficiently high probability. All right, so in fact, this is the best known. Here is the best known results on locally decodable codes. For Q equal 2, the best known trade-off between length and dimension is precisely that given by the first order Reed-Muller code. The bound, which says n has to be greater than something exponential, is actually not too far from that. But as long as you go to more than 2 queries, 3 queries, and so on, you immediately observe there are enormous gaps between the constructions and the bounds. This one says that n is essentially exponential in k. This one says it has to be at least a square of k. All right, so this is really the key open problem in this field, the enormous gaps in this table. Another interesting question to ask is, we know it's not possible, it's been shown, it's not possible to have codes that we're sort of all used to, codes of constant rate. That would mean that n is linear in k. But could we have locally decodable codes where n is polynomial in k, not exponential? And I guess the prevailing conjecture is no, but that's not known. Well, anyway, I think this community is largely unaware of any of this. And there's lots of nice, important problems in this field that I think we could contribute quite a bit. And that was one of the reasons for showing this. Okay. Well, looks like I'll have no time to go through network coding. Apologize for that. Let's skip everything. Aha. Let's get to conclusions. Well, I thought I should really conclude a talk like this on a personal note. I'm not sure whether you recognize this person. Quite frankly, neither do I. But I could tell you who it is. That's me 20 years ago when I started to work in the field of coding theory. So, for 20 years now, it's been really an amazing field. It's been an enormous pleasure to work in coding theory. And I hope I have convinced you, maybe a little bit in this talk, that the field today is as alive as ever. And really, to my mind, it has never been more fun than right now. Well, this I could recognize right away. This is my son, Jonathan. He's 2 years old. You could pay close attention to the title of the book that he's reading. And what I hope is that by the time he's done reading this book, 20 years from now, the field will stay as alive as it is today. And that, folks, is up to you.
Thanks very much for the exciting talk. We will call for questions in a moment, but let me say right away that after the questions, we will have some announcements, so please do not leave. Questions to Alex?
Ready? Oh, this is just a conjecture. No, it's you're talking about the ReedSolomon?
No. You have the theorem there. You said it's very recent that these codes have to be constructed for every channel achieving capacity.
No.
Oh, yes.
Let's get there. Is that what you mean? Yes. Oh, okay. You're talking about the title of the Goswami-Rudra paper? Well, okay. The title of Madhusudan's paper, the original one, before I corrected it, was Maximum Likelihood Decoding Algorithm for ReedSolomon Codes. These are not people from our community. They're not familiar with the terms that we use. So I think the title is certainly not proper in our setting, but in his mind, this achieves the list. So this is the best possible that you can get. This is not what you can do is get to the rate, which is obviously the best possible. But this is just a conjecture.
Other questions, please? Yes? Case?
About ReedSolomon Codes. The applications of ReedSolomon Codes has been, I think, in particular on channels where you see combinations of bursts and random errors. Okay?
Certainly. Certainly.
But in your talk, you only, or I have understood, discussed random errors and forms of random errors. So maybe you can also say
So it's much more difficult.
Repeat the question.
Yes. So the question is whether ReedSolomon Codes or soft decision decoding of ReedSolomon Codes would be good for error model where you have both bursts and random errors. That's hard to analyze, but we have simulations. This is not something that I showed, but it certainly works very well. There are some models, but it would take a long time. There's something called the multinomial model, which looks into bursts, collects statistics on bursts, and then there's an analytical result you can get from that on the performance of soft decision decoding. So it's certainly a valid question. Certainly does work in this scenario as well.
Thank you. Well, we'll probably close it because of the schedule. So Alex, thanks very much again for a very exciting talk.